Thank you, Beth. So that was a really great panel around the National Climate Assessment. Really great questions. I was really impressed by the questions that came up. One of the challenges that we have in the Great Lakes region is that a lot of the information that has come out in the National Climate Assessment, other reports, is centered around the Midwest or the Northeast region. But we are the Great Lakes region. So a lot of our work and effort goes into synthesizing the information across a pretty diverse geographic region that has the Great Lakes as the centerpiece. So Matt Nod and I were giving a talk for the Huron River Watershed Council a few weeks ago, and I got up to talk and Matt pointed at me and he said, "This guy works with a lot of smart people." And he's right. And he didn't realize it, but he was actually including himself in that statement. And a lot of them are sitting in the front row, and you heard a lot of them talk already. So it's a privilege to work with these people and sort of present just an overview of sort of the broad themes we see in the region, the Great Lakes region, synthesizing a lot of information from a lot of detailed work. So here's a figure that many of you have seen before in some shape or form. So we're looking at global temperature here. The black trace is the observed temperatures up to present, and then we have the different projected emission scenarios going out into the future. And a couple things I just want to point out very quickly about this. When we look at the projected temperatures at 2100 and we see there's roughly a 6 or 7 or 8 degree Fahrenheit increase, and then we look at a lower emission scenario and we see 3.5 degrees Fahrenheit, those numbers don't have a lot of immediate impact oftentimes, because you go outside on a 75 degree day or you go outside on a 72 degree day, that doesn't really impact how you're going to behave on that day. But we have to keep in mind that when we look at long-term global average temperatures, each degree amounts to a great deal of energy that we're absorbing into the system. This is also true for our region. And just to put this in context, the temperature change that we've experienced going back to the peak of the last ice age, so back about 6 degrees Celsius, so in the range of 10 to 12 degrees Fahrenheit. So when we talk about these temperature changes, we're talking about something that normally happens over the course of thousands of years, and it's happening over the course of a century and a half, within a generation or two's lifetime. So really dramatic changes in temperature over that period. Another thing I want to talk about is that if you look at this plot up to about 2050, regardless of the emission scenario, those traces don't diverge all that much. That's because the thermal inertia in the atmosphere is going to lead to some warming during that time, just like stopping a freight train. The greenhouse gases that are already up there will continue to warm the planet somewhat into the future. When we look at, planning for that inevitable warming to mid-century is what we call the adaptation space. That's the part of this climate change discussion that we know we're going to have to adapt to in some way. As we go through and think about this, one of the discussions that came up a lot in the questions, and this is something we discuss very often around GLESA when we're engaging with communities. We had the question about how do you talk about this last winter. Differences in the global trajectory, the global trends, regional and local scales. When we think about the global trends, it's a more closed system. The trends are more certain, they have better statistics to back it up. We think regionally, multi-year or decadal changes can be affected by natural variability to a greater degree. And then when we think down to the local scale, where you put a drain, development decisions, all of these things can drastically alter the magnitude of the impacts from climate change that you face. So, just a broad theme to keep in mind. And going back to that regional scale discussion about, the harsh winter we've had, this year was, one of the warmest years, and if El Nino kicks up like it's looking like it might, it could be one of the warmest that we've ever seen globally, despite having that polar vortex outbreak in January. So those kind of issues are important to keep in context. That variability regionally, sub-regionally, and throughout time at different timescales is important to think about. What has changed? We talk a lot about, So what has changed? We talk a lot about average temperatures, average precipitation, but of course we design our systems for extreme events. We manage for thresholds of storms. We build a dam to withstand a 500-year flood or what have you. We're thinking about how to deal with extreme heat. So we have to look at all of these things when we're considering adaptation to climate change. When we look at observed regional temperature, so this is one of the cases where we've been able to pull data across at least the 8 Great Lakes states. So this really is spanning that Great Lakes region, as we've called it. If we go back to 1900, we've seen a 2-degree increase Fahrenheit in average temperatures. You'll notice that temperatures declined from the 1930s up until about 1970. And were clustered pretty low in the early 1960s. So depending on where you start your trend line, that can affect the number that you see here. But generally speaking, average temperatures have increased faster than the national average and the global average. So looking back sort of over our reasonable period of record, where we have good data, we see about a 2-degree Fahrenheit increase. Winter temperatures and overnight low temperatures have tended, in most parts of the region, to increase faster than those annual averages. We looked at projected temperature. We can see this broad gradient south to north. And I think it was Rosina mentioned, for Michigan, we project an 8 to 10 degree Fahrenheit increase. If we sort of broadly look at those high emission scenario models, so there's business as usual emission scenarios, we project, somewhere around 7.5 to 11 degrees Fahrenheit for the region by 2100. And that's looking over both the CMIP3 and the CMIP5 projections. With those warmer average temperatures, we, of course, expect more hot days to be common. We expect this more in the southern parts of the region, and particularly in the southern parts of the Midwest, and in areas where we have heat islands, so urban areas. So looking sort of late mid-century, we expect more 95 degree Fahrenheit days throughout the region, perhaps a month more in southern parts of the region. Michigan and the eastern parts of the basin near the lakes are a little bit shielded from that. So when we look at consecutive hot days, and these are the heat waves that are really dangerous to vulnerable populations because that means the overnight temperatures are not falling typically. So they're not getting that relief during cool evenings, they're getting warmer evenings. So Michigan and the northern parts of the basin, Wisconsin, Minnesota, tend to be a little bit shielded there. So we don't see those increases projected as much, but we do see those very hot heat waves creeping up from the south. We've seen this plot before a few times, so some of these figures you'll be seeing for the third time, but that's okay because there'll be a pop quiz at the end before the refreshment period. So as people have mentioned, we've seen the winter shorten. We've seen the frost-free season grow longer by about 1 to 2 weeks, 9 or 10 days. on average throughout our region, and projected for the Great Lakes, we expect that could be a month or two longer, depending on where you look in the region, by 2100. So a very dramatic potential increase in the length of our freeze-free period and a dramatic shortening and loss of our traditional winter. So the Great Lakes are warming, and to me this is one of the more startling numbers, I think, when we look at our Great Lakes region. So I like to think of the Great Lakes as one of the primary climate engines of the region. They provide moisture for a lot of the lake effect precipitation. They drive lake effect temperatures locally. So if there are big changes to the physics and the behavior of the lakes over time, that could dramatically impact the climate in those areas. And we've seen this 71% decline in ice cover, annual average over all 5 Great Lakes from 1973 to 2010. We do expect after this last winter that that trend will be modified a little bit, but it is still a very rapid decline. As Don mentioned, Lake Superior is warming faster than the nearby air, and that's driving a number of big changes up north to where we expect that by mid-century, Lake Superior in a typical year, so not a year like we just had, but in a typical year, we could see no significant ice cover on Lake Superior by mid-century. If you're coming from Thunder Bay or Marquette, you know just what a dramatic change that would be from the status quo. When we look at precipitation, so with rising temperatures, rising lake temperatures, more exposed lake water for a longer part of the year, we have more moisture available for precipitation, and with those warmer temperatures, that's more energy for convection. And we think that that is contributing to an increase in this regional precipitation, but it is highly variable. And if you look very closely, on a weather station by weather station basis, you'll find a great amount of variability across the region. One example of this, or a couple examples of this, so if you look across the UP, the precipitation, total annual precipitation has been roughly flat or in some places declining slightly, even as lake effect snowfall has increased in some of those areas. If you look at Ann Arbor, which sees some of the largest increases in precipitation across the region, so comparing 30-year averages, so the last 30 years and the previous 30 years, Ann Arbor's seen a 25% increase in total annual precipitation. If you have a research assistant available that can calculate the volume of Michigan Stadium, you can figure out what that translates to in the number of Michigan Stadiums worth of rainwater. And it turns out that, so now Ann Arbor is filling 117 Michigan Stadiums worth of stormwater per year, and that's 23 more Michigan Stadiums than 30 years ago. And all of that water has to be, responsibly managed and discharged back into the ecosystem. But those are a few examples of that variability that we're seeing throughout the region with precipitation. So although we make these broad statements, again, just keep that in mind. And we've seen this before. So these heaviest 1% of precipitation events, this is roughly the threshold, or I should say roughly just above the threshold where we start to see real impacts to infrastructure and stormwater management. So this is where you start to see nuisance flooding, or you start to see U of M students kayaking in the streets. You see ducks floating by windows in Grand River. These are the big storms, and both the frequency and intensity of those storms has increased across the region, more so in the southern extent of the region, like where you see the flooding issues across Iowa, sort of Milwaukee, Chicago, Detroit, in that area. The seasonality of precipitation has also changed. So in general, we see snow being converted to rain, as you would expect with warmer temperatures. So those shorter winters have led to a greater chance of rain than snow. With warmer surface temperatures, we see reduced snow accumulation, so the snow isn't sticking around as long. But, particularly across the north, we've seen more lake effect precipitation events and increased snowfall. And this figure is coming from the Midwest Regional Climate Center, where you can see across the UP, Minnesota, northern Wisconsin, snowfall has increased, but down in the southern extent of the Midwest, the Great Lakes region, southern Illinois and Ohio, Indiana, snowfall has decreased. So very different drivers of climate acting on the region in different ways to give this very mixed result for snowfall. When we project precipitation into the future, we see a broad gradient of most models predicting more precipitation through most of the year, but many of the models project declines in precipitation during the summer months. So when you hear somebody say there's a greater probability of drought, but also a greater probability of extreme storms, that's counterintuitive. That can be one of those communication barriers. One of the shorter answers is that these changes are happening during different times of the year. And also, as we heard from the previous panelists, that water is coming to us in big gulps rather than sips. So there's a greater probability of having a period of drought between those rain events. So if we think just very briefly about what does this mean for the Great Lakes region, we already heard from Crystal Mountain about sort of the loss of snow, the loss of winter tourism and recreation. Don hit on transportation and shipping. People ask us a lot, sort of what are the 2 or 3 big impacts that you would want everybody to know about in the region. And I think you've seen from the panelists these very consistent themes that increasing stormwater, strains on stormwater systems in the southern part of the region. But then as we look into the north, there really is this issue of loss of winter. And what does that mean for the sense of place of a community? How does Marquette, for example, adapt to present itself as a year-round outdoor destination as opposed to a winter destination? So these are the types of issues that we're facing, and as we go through the next panel, the next couple days in these discussions, the question is, how will we adapt to these changes, some of which we know are coming? And that's a question for all of us in the room to answer. So with that, hand it over to Drew.
Opposed to this group is that that boundary does not serve the interests of the water resources in the Great Lakes particularly well. We need paradigms, we need frameworks.